Isomerism. Isomerism, which have the same structural formula but have the different relative arrangements of the atoms or the groups in the space, are called the stereoisomerisms. Stereo means space, meros means parts, and the phenomena is called the stereoisomerism. Stereoisomers are of following two types: conform, conformational isomerism and the configuration isomers. Conformational isomers. Stereoisomers which differ in the relative position of the atoms within the molecules and which can be interconverted simply by rotation about sigma bonds, are called conformational isomers. In other words, the interconversion of these isomers do not require breaking and remarking of the covalent bonds. Configurational isomers. Stereoisomers, which can be interconverted only by breaking and the remarking of covalent bonds and not simply by rotation about the sigma bonds, are called as the configurational isomers. These are of following two types: optical isomerism and the geometrical isomerism. Optical isomerism. Certain compounds can exist in two stereoisomeric forms which cannot be superimposed on one another. In spite of this difference in the relative spatial arrangements of the atoms, these isomers have identical physical properties such as melting point, boiling point, refractive index, density, solubility, etc. They also resemble on one another in most of their chemical reactions. However, they differ only in their behavior plane towards the plane polarized light. One rotates the plane of the polarized light towards the light right, but other towards is the left, but to the same extent. Such a pair of compounds are called optical isomers and the phenomena is called optical activity. Some general concepts about the optical isomerism. In order to understand the phenomena of optical isomerism, we must be familiar with the following terms. First is the plane polarized light. Ordinary light consists of electromagnetic waves of different wavelengths. Monochromatic light, on the other hand, consists of waves of only one wavelength. It can be obtained either by passing the ordinary white light through a prism or grating or by using a source which gives the light of only one wavelength. For example, sodium lamp emits the yellow light of about the 589.3 nanometer wavelength. Whether it is ordinary light or monochromatic light, it consists of waves having vibrations in all planes perpendicular to the plane of propagation of the light. In such a beam of the light is passed through the prism made from a particular crystalline form of calcium carbonate known as calcate. The light that comes out of the prism has vibrations only in the one plane. Such a beam of the light which has vibrations only in one plane is called as the plane polarized light. The nickel prism used to obtain the plane polarized light is called polarizer. Second term is angle of rotation. The angle measured in degrees through which the plane of the polarized light gets rotated on passing through the solution of optically active compound is called angle of rotation. It is denoted by a Greek letter alpha. Polarimeter. The instrument used for measuring the angle of rotation of the plane polarized light is called as the polarimeter. It consists of a light source, usually a sodium lamp, two nickel prisms and a polarimeter tube. The nickel prism near the light source is called the polarizer, while that near the eye of the observer is called the analyzer. The axis of rotation of polarizer is fixed, while that of the analyzer can be changed. In between the polarizer and the analyzer is placed a glass tube called the polarimeter tube, which consists the solution of the optically active substance. The solid lines represents the plane of the polarized light before and broken lines represents the passing through the solution of a optically active substance. If the axis of the polarization of the two nickel prism is held parallel to each other and polarimeter tube is empty, the plane polarized light from the polarizers passes through the analyzer without the change in the intensity. Conversely, if two nickel prisms are held with the axis of polarization perpendicular each other, no light passes at all. However, when the solution of any optically active compound is placed in between the polarizer and the analyzer with their axis of the polarization parallel to each other. The intensity of the light coming out of the analyzer is much less than the falling on the polarizer. In such cases, in order to have maximum transmission the analyzer has to be rotated through some angle in one direction or the other. This angle through which the analyzer has to be rotated to get the maximum transmission of the light is called as the angle of the rotation. The angle of rotation of an optically active compounds depend upon the following factors. The first factor is nature of the optical active substance. Second is concentration of the solution. Third is length of the solution through which the light passes. Fourth is nature of the solvent. Fifth, wavelength of the monochromatic light used. Sixth is temperature of the sample. And the fourth factor are the specific rotation. In order to compare the rotatory powers of different optically active substances, the optically activity is usually expressed in terms of specific rotation. The specific rotation of an optically active substance is defined as the degree of rotation observed when the plane polarized light is passed through a tube having a path length of 1 decameter and the concentration of 1 gram per milliliter of the compound at a specified temperature and wavelength. It is usually denoted by the lambda power T upon D, where T is the temperature, D is the wavelength if the light is used. Usually D line of the sodium vapor lamp having a wavelength of 589.3 nanometer is used as the source of the monochromatic light. Since it is not always possible to dissolve the 1 gram of optically active substance in the 1 milliliter of the solvent, therefore the measurement of the angle of rotation is usually carried out at some lower concentration. While reporting the specific rotations of optically active substance, it is customary to include the concentration of the sodium used for the measurement along with the solvents used for making in the solution marked after the specific rotation. For example, the specific rotation of the cane sugar at 293 Kelvin using D line of the sodium vapor lamp. Next topic, optically active activity discovery. The phenomena of optically activity was discovered by the French chemist Louis Pasteur in 1848. He observed that when a concentrated solution of sodium ammonium tartrate was allowed to crystalline, two type of crystals separated out. Working carefully with a magnifying glass and pair of the pictures, Pasteur was able to separate the crystal into two piles, one of the right and the other of the right-handed and the other of the left-handed crystal. Each type of the crystal, when dissolved in the water, was found to rotate the plane of the polarized light. One solution rotated the plane of the polarized light towards the right while the other towards the left, but to the same extent. Later on, millions of molecules have been discovered which rotate the plane of the polarized light. Such substances which can rotate the plane of the polarized light are called as the optical active substances, and the property of a substance to rotate the plane of the polarized light is called optically activity. A substance which rotates the plane of the light towards the right is called as the dextrorotatory, and the substance which rotates the plane of the light towards the left is known as the laboratory. Chirality. An inspection of the molecular structures of optically active compounds indicates that all these compounds have chiral or dissymmetric molecules. A molecule or an object is said to be the chiral or dissymmetric if it is not superimposable on its mirror image, and the property of non-superimposibility is called chirality. On the other hand, a molecule which is superimposable on its mirror image is called as the chiral, non-disymmetric or symmetric. To understand the terms chiral and achiral, let us consider the alphabet letter P and A, whereas P is the chiral and A is the achiral. Similarly, alphabets letter F and J are chiral while M, O are achiral. The most common example of a chiral object is the human hand. If you hold your left hand before a mirror, the image looks like that of the right hand. If you do not have mirror available, hold your hands together with the palms facing each other. You can see that they are mirror images. Try to superimpose your hands, both palms down. You cannot do it. Thus, human hand is chiral. Similarly, gloves, shoes, and chiral objects. Have you ever thought, why can I hear the left-handed glove in the right hand? This is because they are non-superimposable mirror image of each other. A button, a sphere, a cube, and the most shocks, on the other hand, are achiral since they are superimposable on their respective mirror image. Next is the molecular chirality and asymmetric carbon. Let us extend the concept of chirality to organic molecules. The chirality in organic molecules arises due to the tetrahedral nature of the carbon, that is, four valency of the carbon are directed towards the four corners of a regular tetrahedron as proposed by J. Vance Hoff and C. Le Bel independently. To illustrate this, let us consider a molecules of 2-chlorobutane. In these molecules, C2 carbon is attached to the four different substituents such as H, hydrogen, chlorine, methane, and the ethane. Such a carbon atom which is attached to the four different substituents atoms or groups is called asymmetric carbon atom or the chiral carbon atom or simply a chiral center. A chiral carbon atom is indicated by the asterisk. Further, it may be noted that it is the carbon which makes the molecule disymmetric or the chiral explained below. The mirror image of the A is A1. To check the superimpossibility of the A1 over the A, rotate the molecules through the 180 degree in such a way that carbon chlorine bond in new structure A2 projects the same direction as that in the structure A. Now superimpose A2 over the A. We find that A and A2 are not superimposable. No matter how we turn and twist the molecules without breaking bonds, we may get the central carbon atom and the two of the atoms superimposed. For example, hydrogen and chlorine can be superimposed, but the spatial orientation of methane and the ethane groups are different in the A and A2. In structure A, ethane is pointing towards you, while in the A2 it is pointed away from you. Thus, A and A2 are no superimposable mirror image and hence 2-chlorobutane is a chiral molecule. However, if two substituents atoms or the groups attached to the carbon atoms are similar, the chirality or dissymmetry is lost and the molecule becomes symmetrical or achiral since a simple rotation through the 180 degree chloropropane and its mirror image B1. To check the superimposibility of the B1 over the B, rotate the molecules through 180 degree Celsius 180 degree to get the B2. Now try to superimposable structures B2 over the B. You will find that B and B2 are superimposable. Hence 2-chloropropane is the achiral molecules. From our discussion, it follows that chirality probably arises due to the presence of the asymmetric or the chiral carbon atom. As we shall discuss later in this unit, that this statement, however, it is not always true. Nevertheless, the presence of one chiral or asymmetric carbon atom in the molecules always makes it the chiral and hence optically active. Next is elements of the symmetry. The superimposibility of an object or molecules and its mirror image can be tested with the help of the three elements of symmetry such as plane of symmetry, center of symmetry, and alternating axis of the symmetry. Chiral objects or the molecules do not have the elements of the symmetry. On the other hand, achiral objects or molecules have at least one or more the elements of the symmetry. First is plane of the symmetry or mirror plane. The most commonly observed element of the symmetry is a plane of the symmetry or the mirror plane. It is defined as imaginary plane which divides the molecule into two equal halves such that one half of the molecule is mirror image of the other. It may pass through the atoms, between the atoms, or the both. Thus, a sphere is achiral since it has a plane of symmetry. On the other hand, human hand is chiral since it has no elements of the symmetry. A vertical plane has been shown, but it is not a plane of symmetry since it divides the hand into two unequal halves. Like objects, some molecules also possess the plane of the symmetry. For example, 2-chloropropane has a plane of the symmetry which is perpendicular to the plane of the paper and passes through the chlorine, carbon, hydrogen atom. Similarly, mesotartaric acid has a plane of the symmetry which is perpendicular to the plane of the paper and passes through the point of the carbon-carbon bond. Therefore, both these molecules are achiral since they can be superimposed on their respective mirror image and hence are optically inactive. On the other hand, molecules of the 2-butanol and lactic acid do not have a plane of the symmetry and are achiral and are chiral. As a result, they cannot be superimposed on their respective mirror image and hence the optically active. Second factor is center of the symmetry. A center of the symmetry is defined as a point from which the lines, when drawn on the one side and produced an equal distance on the other side, will meet identical points. It is also called the center of the inversion and is usually denoted by the CI. Third factor is alternating of the symmetry. Alternating axis of the symmetry. A molecule is said to possess an n-fold alternating axis of the symmetry if rotation through an angle of 360 upon n about this axis and then followed by reflection in the plane perpendicular to the axis gives the molecules which is indistinguishable from the original molecules. Consider, for example, molecules shown here as Z plus and Z negative represents the chiral group such as positive charge and the negative respectively. Rotation of the molecules through the 90° about the axis AB passes through the center of the ring and the perpendicular to its plane gives the molecules B. The reflection of the B gives the original molecule A. Thus, the molecule has the fourfold 360 upon 90 is equal to 4 alternating axes of the symmetry and hence it is called the achiral. Relationship between asymmetry, dissymmetry and the chirality. First is it is interesting to note that while describing the optical activity of the organic compounds, two terms asymmetrical and disymmetry have been used without any distinction, yet there exists a subtle difference between them. Molecules which has no elements of symmetry or alternating or simple axis of symmetry is called asymmetrical molecules. Such a molecule is usually optically active. On the other hand, a molecule which has no alternating axis of symmetry but may or may not have a simple axis of symmetry is called as the dissymmetric molecules. Like asymmetric, dissymmetric molecules are also usually optically active. Consider the example 2-butanol. It has no element of symmetry. Now consider the projection formula of optically active tartaric acid. It has a simple axis of the symmetry in the center of the molecules. It is shown by a dot and passes perpendicular to the plane of the paper. Rotation through the 180° about this axis gives the formula second, which coincides with the original formula first. Thus, optically active tartaric acid has the simple or C2 axis of the symmetry. Hence, it is not a asymmetrical molecule, but it is disymmetric molecule. Stereogenic center or the stereocenter. We have stated about the tetrahedral carbon atoms attached to the 4 different atoms or the groups called the asymmetric or the chiral carbon atom. However, in 1984, K. Mislow and the J. Siegel pointed out that the use of the term chiral carbon atom has created conceptual confusion. According to their scientists, it is not that the atom which is chiral, but actually it is the molecules which is chiral. In other words, chirality is a geometric property which pervades, extends and affects all the parts of the chiral molecule. For example, all the atoms of 2-butanol are in the chiral environment and hence all are said to be the chirotropic. However, we have not used the term chiral carbon atom such as carbon 2 of the 2-butanol in the same sense. We have simply used in this term to indicate that if any two groups attached to this carbon are mutually exchanged, a new stereoisomer is formed. In other words, of 2-butanols should be designated as the center of stereoisomerism or stereogenic center and not a chiral center. Further, consider the cis and the trans stereoisomers of the 1,3-dichlorocyclobutane. Here, carbon atoms 1,3 are the centers of the distereoisomerisms but are not the chiral centers, since carries two identical groups. Therefore, these are preferably called as the center of the diastereomerism or the stereogenic centers. The stereogenic centers may or may not be the chiral. For example, the stereogenic center, that is carbon 2 in the second butanol, is chiral, but C1 or C3 in the cis or trans 1,3 dichloromethane is the achiral. Thus, all the chiral centers are the stereogenic, but all the stereogenic centers are not the chiral centers. Optical isomerisms in the compounds containing the one chiral center or one stereogenic center, or simply called the inisomerisms. Optical isomers which are not superimposable mirror image of each other are called as the isomers, and the phenomena is called as the inisomerism. The inisomers have the identical physical and the chemical properties but rotate the plane of the polarized light in the opposite directions, but to the same extent. To understand the phenomena of the inisomerisms, let us again consider the molecules of bromochlorofluoromethane. It exists in the two stereoisomeric form, first, second, which are non-superimposable mirror image of each other. Further, each of two isomers is optically active and rotates the plane of polarized light in the opposite directions, but to the same extent. Thus, first and second represents the inisomers of the chlorofluoromethane. The inisomers which rotates the plane of the polarized light towards the right is called as the dextrorotatory, and it is represented by the D, while the inisomers which rotate the plane of the polarized light towards the left is called as the levorotatory, and it is represented by the L. However, it may be emphasized here that it is not possible to tell as to which isomers, positive or negative, just by looking at the structure. It has to be determined only by experiment. Conditions for the inisomers. It may be noted that the necessary and the sufficient conditions for the molecules to exhibit the isomerism and hence optical activity is chirality or dissymmetry of the molecules. That is, molecules and its mirror image must be non-superimposable. It may or may not contain the chiral and asymmetric carbon atoms. Usually, the presence of one or more the chiral carbon atoms causes the molecules to show the inisomers and hence optical activity, but certainty is not the necessary and sufficient conditions. For example, mesotartaric acid contains the two chiral carbon atoms marked by the asterisks but does not show the inisomers, and it is usually optically inactive. This is due to the reason that it contains a plane of the symmetry which divides the molecules into two equal halves, so that one half of the molecules is a mirror image of the other. As a result, mesotartaric acid and its mirror image are superimposable. In other words, mesotartaric acid in an achiral or non-symmetric or disymmetric molecules, and hence it does not show in isomerism or optical activity. Thus, the optical inactivity of the mesotartaric is due to the internal compensation, that is, the rotation caused by the one half of the molecule is exactly cancelled by the equal and opposite rotations caused by the other half of the molecules. On the other hand, there are many compounds which do not contain the chiral carbon atoms, but their molecules are chiral or dissymmetric and hence show the inisomerisms or optical activity. For example, in the allenes and distributed diphenols do not contain the chiral carbon atom, but their molecules are non-superimposable on their respective mirror image and hence show inisomerism and the optical activity. Properties of the inisomers. The most important properties of the isomers are given the below. They have identical physical properties such as melting point, boiling points, density, solubility, refractive indices, etc. They differ only in the direction of the rotation of the plane polarized light. One rotates the plane of the polarized light towards the right and the other towards the left, but to the same extent. Inisomers have identical chemical properties except towards the optically active reagents. Third, isomers have different biological properties. In biological systems, all the reactions are catalyzed by the enzymes which themselves are optically active compounds. The reactions of the isomers which with the enzymes are so stereospecific that quite often the reactions with one of the isomers do not take place at all. For example, we eat lot of the dextrorotatory glucose in the form of the carbohydrates daily. This is metabolized in the body to produce the CO2 and H2O, and a lot of the energy is generated. This energy we use for our day-to-day work. However, if the liver rotatory glucose, it is not metabolized and excreted such as through the urine. Similarly, quinine brings down the malaria fever but not the positive quinine. This difference in the reactivity of isomers is of the great importance in the biochemistry and the chemistry taking place in our body. Chiral or achiral molecules with the two stereogenic centers. So far, we have discussed that in the presence of the one stereogenic centers or the chiral asymmetric carbon atoms makes the molecules disymmetric or chiral. As a result, the compounds containing the one stereogenic center or the chiral carbon atom can exist in two stereoisomerisms called the isomers. Therefore, it is accepted that the compounds which contain two or more the stereogenic centers would exist in the more than the two stereoisomeric form. Let us discuss the optical isomerism of the compounds which containing the two stereogenic centers. These two stereogenic centers can be either dissimilar or the similar. Next, compounds with the two dissimilar stereogenic centers or the diastereomers. Stereoisomers first second are non-superimposable mirror image of the each other and hence represent a pair of the isomers. Thus, the compounds containing the two dissimilar stereogenic center exist in the four optical isomers which can be regarded as the two pairs of the isomers. Now, the question arises to what is the relationship between any other pairs such as first, third, first, fourth, second, third and the second, fourth. As inspection of these structures reveals that none of these pairs are the mirror image of the each other are called as the image of the each other, nor can they be interconverted by the rotation about the carbon-carbon bonds. Such stereoisomers which are not the mirror image of the each other is called as the diastereomers or simply called diastereomers. Thus, first and the second, first, third, first, fourth, second, third, or the second, fourth all represent a pair of the diastereomers. In other words, diastereoisomers are stereoisomers which are not the isomers. They have the same configuration at one center or the chiral carbon atom, but different the other. Next is properties of the diastereomers. First is the physical properties. Melting point or boiling point. Unlike in isomers, diastereomers have also different physical properties such as melting point, boiling point, solubilities in a given solvent, densities, refractive indices. Separation. Due to the differences in physical properties, diastereomers, unlike isomers, can be separated by the physical method of the separation such as fractional crystallization, fractional distillation, and the chromatography, etc. Second point is behavior towards the plane polarized light. Diastereomers may be either optically active or inactive. For example, geometrical isomers which are also regarded as the diastereomers which are optically inactive, which others are usually optically active. Even the optically active diastereomers may have the same or the opposite signs of the rotation. Third point is chemical properties. Unlike in isomers, diastereomers have similar but not the identical chemical properties. Thus, the rate of the reactions of diastereomers with chiral or achiral reagents are generally different. This is due to the reason that neither the reagents nor the transition states are mirror images of the each other. As the result, diastereomers have the different energies of the activation for a particular reaction and hence react at the different rates. Optical isomerism in compounds containing the two similar stereogenic center or simply called the mesocompounds. Stereoisomers first second are the mirror image of the each other. They are neither superimposable nor interpretable by the rotation about the carbon-carbon bonds. What are the mesocompounds? Mesocompounds, the stereoisomers which are optically inactive compounds whose molecule is superimposable on its mirror image in spite of presence of chiral carbon atom is called as the meso compound. It may be noted that meso compound is optically inactive because the rotation is caused by the one of the molecules is exactly cancelled by the equal and opposite rotation caused by the other half of the molecule. In the other words, optical activity of the meso compounds is due to the internal compensation. On the other hand, the optical inactivity of a racemic modification is due to the reason that the rotation caused by the molecules of the one isomers is exactly cancelled by the equal and opposite rotation caused by the same number of the molecules of the other isomers. In the other words, the optical inactivity of the racemic mixture is due to the external compensation. Relationship between the isomers and the meso compound. Let us again consider the three stereoisomers of the tartaric acid. An inspection of the structure of positive tartaric acid and negative tartaric acid and mesotartaric acid reveals that they are not the mirror image of the each other. Can they be interconverted by the rotation about the carbon-carbon bonds? The positive tartaric acid, mesotartaric acid are the diastereomers and so are levotartaric acids and the mesotartaric acids. Being diastereomers, the properties of the mesotartaric acid are different from those of the positive tartaric acid and the negative tartaric acid. Racemic modification or the racemic mixture. When equal amount of the two isomers are mixed together, it gives an optically inactivity form called the racemic mixture or the racemic modification. It is denoted by the prefix positive, negative or RS before the name of the compound. For example, if equal amount of the positive lactic acid or the negative lactic acid are mixed together, we find the racemic mixture positive, negative or RS lactic acid. A racemic mixture is always obtained whenever a chiral or the dismetric compound is synthesized in the laboratory from the achiral. This is due to the reason that they are equal probabilities for the formation of the two isomers. For example, consider the formation of the 2-butanol by the nickel catalyzed addition of hydrogen. The carbonyl group is planar, therefore hydrogen absorbs on the surface of the nickel crystal can add with the equal ease on the either phase of the 2-butanol, whereas the addition at the one phase produces the other isomers and the two reactions occur at the same rate. A racemic mixture is always optically inactive because the rotation caused by the molecules of the one isomers are exactly cancelled by equal and opposite rotation caused by the same number of the molecules of the other isomers. Racemization, the process of converting of an isomers of a actively compounds to the racemic mixture is called as the racemization. Racemization is normally an undesirable process and hence whenever any reaction is carried out on an optically active compound, it is necessary to avoid such reagents or the reaction conditions which induce the racemic mixture. Racemization can occur either by the heat, chemical reagents, acids, bases, or even by the contact with the polarization. Some of the most important mechanisms by the racemizations are: first is the by the rotation about the carbon-carbon single bond. The optical activity of the ortho-substituted diphenyl is due to the restricted rotation about the carbon-carbon single bond joining the two phenyl groups. The cause of the restricted rotation is the presence of bulky substituents at the ortho positions of the two phenyl groups, while prevents them in assuming the planar transmission states. These compounds undergo the racemization. Next topic is resolution. As stated above, a racemic mixture contains equal amounts of the two isomers. The process by which a racemic mixture can be separated into positive or negative isomers is called as the resolution. Since the isomers have the identical physical and chemical properties except towards the optical active reagents, they cannot be separated by the usual techniques such as fractional crystallization, solvents, or optically active, fraction distillation, chromatography. Some of the important methods to resolve the racemic mixture are discussed below. First is the mechanism separation. This is the most classical method and was used by the Pasteur to separate the isomers of sodium ammonium tartrate. Sometimes when a concentrated solution of a racemic mixture is allowed to crystallize, two types of the crystals may separate out, one type being mirror image of the other, and these two types of crystal can be separated by the hand picking using a pair of tweezers and a magnifying glass of a microscope. Limitations: this method is most laborious and time consuming, and it is applicable to only those